Hello, I'm Neil Storey.
I'm Lacie Keitz.
I'm Ryan Thompson.
And I'm Willie.
And we're students here at Dixie State University. Our coach is Vinodh Chellamuthu. We're solving problem B, which is the spinning wheel with a bird.
Here's a quick video of what our mechanism is replicating.
This page at the end. Where is that?
In the next slides, I'll be going over observations of how the bird is moving around the wheel and the changes of the bird's motion and angles as it spins to show what the bird is doing.
This page at the end. Where is that?
The bird is centered on the wheel at this point when its feet and body are aligned over the wheel at the top. Notice that the angle of his feet centered on the wheel is 90 degrees. By using the center of mass equation, we are able to find the center of mass at this point. The bird finds its center of mass before spinning, but when it's ready to spin, he hooks his feet to the outside of the wire, shifting its center of mass to the outskirts of the wire. The bird's angle also shifts to 30 degrees. The bird is now teeter-tottering on the edge. This gives the bird great potential energy for its spin. The bird turns its head to the left to counteract the lean to the right and leans into the swing, giving the bird enough force to start its acceleration. By using the Newton's second law equation, force equals mass times acceleration, we can find the force acting on the bird. We can find the acceleration also by using the equation acceleration equals final velocity minus initial velocity divided by time. Notice the bird's angle changes from 30 degrees to 0 degrees as it starts to spin. Gravity at this point becomes another force pushing the bird into its spin. The bird's angle changes from 0 degrees to 330 degrees to 315 degrees to 270 degrees to 225 degrees, and eventually the bird goes back to 90 degrees when it returns to the top. At the bottom of the wheel, the bird tucks its body in as if it's surrounding the wheel. The bird brings its mass towards the center of the wheel, which increases its kinetic energy and further allows the bird to get back up the other side. We have thought of a mechanism that replicates the bird's motion doing a full revolution.
We modeled an arbitrary mass revolving around a vertical circular track to get a clearer understanding of how the bird may gain energy and momentum as it goes around the wheel. The first example is a single 1 kilogram mass on a frictionless surface. As you can see, the kinetic energy at the bottom is equal to the potential energy at the top. So the ball would return back to its original location at its original speed. The second example shows a 1 kilogram ball falling, and then at the bottom of the track, the 1 kilogram instantly changes to a half kilogram and continues up the track. If there's conservation of energy, then the ball would return back to the top with some additional kinetic energy. Work done to the ball is equal to the kinetic energy added to the system. If there was energy lost due to friction and inertia of the system and no change in mass, the ball wouldn't make it back to the top. But if there was work done or a drop in mass, the ball could make it to the top. What is shown is that the energy lost is equal to the energy gained by the changing mass. Mass is analogous to inertia, and though the bird can't decrease its own mass, it can decrease its own inertia. And that is how it can return back to the top with frictional and inertial losses.
A radial slide is the simplest functional mechanism. It recovers potential energy by lifting the mass as it passes the top and bottom zenith, and generates kinetic energy by varying the moment of inertia throughout the rotation. It cannot generate energy from rest if started at the bottom of the wheel. A tangential slide can generate energy from this initial condition, but it generates less potential energy than a radial slide at certain critical conditions. An offset radial slide can both start anywhere from rest and generate a large amount of energy, but other mechanism ideas developed later can generate more energy. Rotating around a point at the perimeter of the wheel can generate energy from any initial condition. It can also recover potential energy at any point throughout the wheel's rotation, unlike the previously discussed radial slide or its variations. It can generate kinetic energy efficiently as well. Its motion is restricted by the nature of its movement, so control and mathematical modeling is difficult. The last and most versatile option is a combination of radial translation and rotation. This type of mechanism generates energy in all conditions, can generate energy from every conceivable initial condition, and is more simply modeled and controlled than other options. Potential energy is recovered at the top and bottom of the wheel's rotation by sliding a mass upward. This gain in height increases potential gravitational energy. Kinetic energy can be generated by reducing the overall radius to the mass. This reduces the moment of inertia to the mechanism. Our mechanism combines radial translation and rotational motion to vary the overall distance as a function of the mechanism's rotational position as it relates to the wheel, and a change in the mechanism's translation as a function of its rotation. Our mechanism is designed to vary its motion greatly, both based on different initial conditions and throughout the development of a full rotation, as shown by these videos. The first video shows the mechanism starting from rest at the bottom of the wheel. It generates motion by offsetting its center of mass. The second and third videos show that at low amplitudes, the potential energy gained from simply shifting mass upward is likely the most efficient way to generate energy. The last video shows that at high rotational velocity in a full rotation, varying the moment of inertia may be the best way to gain energy. Gravitational torque affects both friction and rotational velocity. Its radial and tangential components are functions of the machine's angle above vertical. When the machine is at the bottom of the wheel's rotation, gravity acts in a purely radial fashion. This contributes to increased friction, but decreases the effect gravity has on rotational velocity. Conversely, when the machine is at either side of the wheel at 90 degrees, the gravitational force is expressed entirely tangentially. Here, the normal force acting on the hub and contributing to friction loss is based purely on radial acceleration due to rotational speed. At this position, the tangential force acts only on rotational velocity. Actual friction loss is a function of the normal force against the hub, which varies with both gravitational torque and rotational speed. For simplicity's sake, we assume friction is constant and serves as the main loss of energy for the system. We are also choosing to neglect drag.
Using SOLIDWORKS, we designed a mechanism that we feel will best approximate the motion of the wheel as the bird drives it. The mechanism has two wheels comprised of both an inner and outer wheel connected using supports. The wheel can be mounted vertically just like in the original video. Two arms are fixed at a point on the wheel with an attached mass that moves to replicate the motion of the bird. We will control the mass's motion using a system of stepper motors, cables, and sensors. Using this machine, we could run a number of tests starting the mass at any point and using the sensors and motors to control the lateral and or rotational motion of the mass at any point along the main wheel's rotation. This animation shows the lateral motion of the mass along the fixed arms attached to the wheel. The stepper motor will control the up and down motion, and springs will force the mass up along the arms. Here we show the rotation of the mass about the pin perpendicular to the wheel. Again, a stepper motor will be used to control the rotation and the direction of the mass in either the clockwise or counterclockwise rotation. Thank you for watching our video. We hope that you enjoyed watching it as much as we enjoyed making it.